Okay, this last one is to help you out on the homework, and it's real similar to what you'll be doing in 15110, right? You've got a box that weighs 8 pounds going around, but it's decreasing its radius. It's getting pulled in, and it's initially starting out 5 feet per second going around, right? So we're saying if the rope is pulled inward constantly, then what is its uh, how much work is done after pulling in the rope from A to B. So that's kind of interesting. So we're solving this for work, right? Pound feet is probably what we want, a force times a distance. So this is a little interesting because we're combining it with our work and energy. So let's see if we can think that through. Remember, our work and energy was something like start out with a certain amount of kinetic energy plus whatever work changes that kinetic energy, right? We change our velocity and we end up with a final kinetic energy. So if this is 1/2 mv1 squared plus the work equals 1/2 mv2 squared, what we're looking for is that term right there. So we need its initial velocity and we need its final velocity. We know its mass. So we could go and solve for that using our momentum equations. So if we're going to do our angular momentum, mv1 d1 plus whatever change in, and I should make that an integral, the integral of moment times time, mdt, equals mv2 d2. So we need to think to ourselves, do we have initial velocity? Yes, so this is not going to be zero this time. Do we have applied moments? If we look at our picture, huh, no forces pushing the block. This is pulling it inward, but it's not changing its velocity tangentially, right? So that is not there. There's no motor spinning it around or something applying a torque or a moment in the middle. So yeah, there's no actual applied moments like there was in previous problems. So that's an interesting twist. This is actually going to be zero this time. And then we've got a mass times the velocity d2, our final angular momentum. And yeah, we'll have some of that. And that's what we're looking for is what is that v2 so that we could plug it in there and end up solving for that. So let's see, let's come up with our angular momentum here. We've got the angular, or we've got the mass of 8 pounds divided by 32.2. That's in slugs now. We've got our tangential velocity, which is what we want, 5 feet per second. And we've got our distance to the center of rotation, which is 2 feet to start with. Plus the zero equals the mass again. And really those are going to cancel out, so we didn't need to put that much effort in, but that's all right. V2 we don't know. And that would be really the tangential velocity too. It also has the inward 4 feet per second, so we got to be aware of that. And then we've got the distance to that center of rotation again is now 1 foot. So with that, we could get the tangential velocity 2 equals 10 feet per second. That's what we'll get there. Okay. So is that the V2 that we need to stick in here? That's only this tangential velocity, right? It also, or it's going to have this constant 4 feet per second. So if we want to come here and do our V1, V2, we should probably come up with a total V1 and a total V2. So if we've got initially 5 feet per second squared plus the V1 is pulling inward 4 feet per second, which gets squared. we've got 6.4 feet per second initially of total velocity that'll contribute to her kinetic energy. We've got V2 was 10 feet per second tangentially, but it also has the 4 feet per second going in the normal direction. So that'll get us 10.77 feet per second. So a little more than just that 10. And so with that, now we can come back and do our work and energy and solve for our work term. So 1/2 mass times V1 squared plus the work, which we're looking for, equals the final kinetic energy 1/2 m times V2 squared. Put it in your solver or do a little arithmetic. You solve for the work equal to 9.32 pound-feet. All right. So try that one out. In the homework, it'll be similar, and you can come up with, I can't remember what it is, if it asks you for something different. It might ask for a change rate, a change in radius, what it has to be to attain a certain speed, or you can do various variations to be redundant there of this type of problem. But that's a pretty good one. And that is it for chapter 15. And so if you're doing it online, you'll have a chapter 14, 15 exam coming up, and you can study for that and look up the videos for the sample problems there. And if you're in class, you'll have the lab that you'll need to do um, instead of your classical test.